So I've got one of the old Rev 1 boards, and this is the Rev 2 board. You can see some of the bodgers that were required to make the old one work quite as well as I wanted. I had some issues with the voltage regulator that I originally wanted to use when you're powering this thing off external power. And what was happening was, firstly it was running screaming hot, despite leaving, you know, quite a large thermal area for it to sink heat away, and it was manifesting as a sort of audio tone in the audio codec chip, so you were hearing it on the radio and through the computer system. And I poked and prodded at this with the scope for a long time to try and track this down, and eventually found it on the voltage regulator. I couldn't really understand it. So just really quick, I mean, I've got a load of other voltage regulators to try, and so I swapped the little SOTS 23, I think it is, package one that I had here for a nice big TO220, and the audio tone went away, but it still ran a little bit hot. And so what I decided to do was split the power supply rail so that all of the audio amplification stuff would be on one voltage regulator, and all of the logic stuff, all the USB stuff, would be on another voltage regulator. And it had helped to split the heat, and it would stop the tone from getting through onto the audio side of things. So here you can see a bit of copper clad board. If I flip this around the other way, what I've done is I've soldered a couple of TO220s to a bit of copper clad board. I mean, they share the same, the tab on these is ground, so it's okay for them to be soldered together. It all shares the same ground anyway. It's just to act as a little bit of a heat sink. It ran acceptably well. I mean, sort of the surface of that plate was something like 60 degrees centigrade, but it was still a bit hotter than I'd like, really. So there was that, and also there was a problem with the serial port that I'd put on here. It was holding the PTT high constantly, so if you just plug this interface in, your radio would be transmitting. You'd have to go into some sort of software, something like Free Radio Network or EQSO or whatever it is that you use if it's doing it through COM port keying, and reverse the logic, set it as active low. And that made the problem go away. But the moment you come out of that software, or if you use some other software like Zello or TeamSpeak or whatever the case may be, it could be that you'll use something that doesn't have serial port control, and so you wouldn't be able to flip the logic that way. The moment you come out of your program that uses serial, it reverts back to its old tricks. There was a couple of different ways I could have bodged this in hardware, but it would have resulted in it being quite ugly with bodge wires going all over the place and everything. And I thought, you know, it's a little bit unfair for something that's supposed to be custom designed and addressing issues from other interfaces. It's a little bit unfair to release something that's got loads of bodge wires all over it. Okay, so that's the stuff. Those are the main issues that I was trying to sort on the Rev 1 board. It's a shame because I ordered a lot of these because it worked out cheaper that way. This 99% works if we get rid of the serial port keying. If somebody just wanted this as a Vox board, then it would work that way. Absolutely no problem whatsoever. Oh yeah, by the way, that was another dumb mistake, and I can't understand how I managed it. On this board, the serial port that's on here, I wanted people to be able to access it through a normal DE9 connector. So you'd be able to plug a radio into here and program the radio up using the interface as a serial port. And what I did, what I thought would be clever, is to connect the USB to serial converter. The traces just run along the board and straight into this DE9 connector. Well, of course, this is TTL logic. So you know, that was never going to work for plugging regular RS-232 devices into this socket. So how I managed that, I really can't explain myself, and that's another reason for vanishing this and never speaking of it again, and doing it again but properly this time. Okay, I'll get rid of this board out of the way and we'll zoom in here for a closer look. Right, so this is the REV2 board in a little bit more detail. The main differences being, this time the power supply has been modified basically. It's no longer going to be powered by USB. I just couldn't clean up the power supply without upping the cost fairly dramatically. No matter how I tried to do it, it started to get expensive. So basically what I've elected to do is no longer power it from USB at all. There's no option to power this from USB. It's powered from an external power supply, and the idea would be that you would power it from the same power supply that you're already powering your radio from. This entire device draws no more than 250 milliamps at full chat. So, and that, a lot of that is from the relay, whether or not you choose to have a relay or an opto isolator. You may have some special need for a relay for the PTT. If you want a relay, that can be done. I've put a footprint in there, as you can see. But for what I'm doing here, I've just got an opto isolator for the PTT, and that obviously draws significantly less current than the relay. The relay coil is almost 100 milliamps. Okay, so the power supply comes in and it goes to two linear voltage regulators now, both of them 5 volt, and so you can stick into here just about anything you want between 7 and, I forget, I'll have to have a look at the data sheet, something like 17 volts. So if you're powering it from your bench power supply at 12, 13 volts, that's perfectly fine. The higher a voltage you put into here, the hotter these are going to run. This one runs absolutely clap cold all the time because it's not doing any work, and that's why it's just folded over on the board. What you'll notice is that I've left this space here, and it looks like I left this space so that I could fold the regulator over. Actually, the way that I've done it is I've laid it out in such a way that the regulator could sit upright and you could have a large heatsink behind it. This heatsink is bolted to the actual board, and there's a large thermal pad area, there's some thermal grease under there, and this top copper pad is tied with a load of wires through to the ground plane underneath to try and suck away some of that heat. So that's quite a big heatsink. And it runs at a reasonable temperature now, sort of 55 degrees centigrade on the metal part of the tab. I'm going to run this and just see how it goes. And it's given me an idea for our first hack video, and that would be to put a linear temperature sensor, something like an LM35, sort of epoxy resin that onto the case here, and power it from the board. And its input could go into one of the analog inputs on the microcontroller, and then through the serial port, through USB, we could pull up a terminal window and look at what the temperature is on here, just whenever we choose. So that might be a good example of a first sort of hack video, if you like. Other differences here, so yeah, I've already mentioned the fact that I've laid out an area here. In fact, the relay always existed. What I've done is I've modified it to add the ability to put an opto isolator in there instead. The two transformers have been moved apart from each other because I've ended up with some room, and I thought rather than putting the pads on the other side of the transformers and having the transformers next to each other, why not separate them with some space to try and magnetically decouple them as much as possible. So I've put the sort of prototyping area in between the two of them. What else do we have here? Oh yeah, so there's the addition of you've got USB comes in and it comes to a USB hub. I'm using 3 of the ports on this USB hub. It's a 4-port hub. So the first port is this USB to serial converter. It's an FTDI chip, and this is basically connected to a MAX 323 logic shifter and then through onto the serial socket. So what you'll be able to do is plug a radio into here and program the radio, or you could plug any other serial device you want into here. It doesn't have to be anything to do with radio. You could plug any serial device into here, and this socket will act the same as a serial socket on the back of your desktop PC or whatever it is that you've got. The RX and TX and RTS from this USB to serial converter, I've put through some headers here, some jumpers, and what you're able to do is change the destination of those pins. So if you are using this as a kind of external USB to serial converter, these 3 jumpers, you would move them over to the position marked DE9, because this is a DE9 connector. If you are wanting to communicate with the microcontroller, then you put the jumpers in the position that they're in right now, and the TX, RX and RTS are then connected to the microcontroller, and you're able to program the microcontroller through the USB port and all that good stuff. You're able to sort of observe the serial port in the microcontroller. So at the moment I've got this sending debug information, and I'm able to look at that through a serial terminal window. So that's one of our USB ports covered. The second USB port is another USB to serial converter. This one is just for COM port keying only. What I've done is I've broken out all the pins onto a header here so that you can still access them and you can still do things with them if you'd like, but basically the DTR and DSR are fed into the logic train for such purposes as running software like EQSO or whatever for COM port keying. And the reason behind that was, the reason that I've got 2 USB to serial converters is I couldn't figure out a particularly good way of separating sort of radio activity from getting to the microcontroller. It turned out easier and cheaper just to stick another USB to serial converter. I mean, I've got another port on here anyway, so I might as well. The third and last port is the USB audio codec. In other words, the sound card. It's a Texas Instruments PCM 29 series IC. So I've broken out the unused audio port here on a header. The other one goes through to all the amplification clobber that's down here. And so we've got a large on-off switch, an LED indicator to tell you that it's on, a TX LED to tell you that the PTT has been activated, an RX LED to tell you that you're currently receiving traffic. There's a potentiometer to change PTT delay. There is a TX and RX dial to change incoming and outgoing audio volumes. They also have internal trimmers so that you can adjust the range of these potentiometers. Also, within here is a VOX circuit. There's actually 2 VOX circuits. So if there is audio coming from what I'm going to call the internet, say your program, TeamSpeak, Zello, whatever, this behaves in a similar fashion to the way that the signal link would behave, where incoming audio triggers a VOX circuit and that activates the PTT for you. and it activates it for as long as the TX dial is set to sort of respond. If you've set this to 1 second, then 1 second after silence begins, the PTT will drop out. The way that I've programmed this at the minute, it has a range of 100 milliseconds up to 5 and a bit seconds. With some reprogramming on the microcontroller, you can adjust it to whatever you like, whatever range you'd like. But sort of, and it would be very easy to have the minimum on this set to 0, but just for my own purposes, that's the way I have it set right now. I'm trying to think if there's anything else of use or note here. There's a couple of unused pins on here. Most radio amateurs won't find a great use for these two pins. There's accessory 1 and accessory 2. Accessory 1 and 2 would be used for things like linking Tetra radios. I won't go into too much detail here, I guess it'd be better covered in another video. But they are also indirectly linked to a position here for another opto isolator, and that can then be fed as logic into the microcontroller to do funky stuff with, either input or output. This connector is a 10P10C connector, it's not 8P8C. Ethernet, which is what most people will be used to, is 8P8C. It's got 8 connectors in it. This is 10-way, it's got 10 connectors. And that's to cover everything. Everything is run as balanced line up to this socket. What you do with it after that is your concern, but my advice would be to keep everything separate and run everything as balanced line back to the radio. It helps with crosstalk, and indeed some radios demand that some of the return lines are separate. So for instance, some Tetra radios, the return lines are separate. An example of this might be that on some of the Tetra radios that are out, the radio ground, which is 0 volts, which is the negative terminal of your power supply, is normally what the PTT is referenced against. But the audio stages are balanced line. They're not 0 volt referenced, and tying them to 0 volts is not going to end well, let's put it that way. The interface will be just fine, it's not going to do anything to this, but I can't make any guarantees about your £800 or £900 Supura Tetra gateway. So that's why there's so many connectors on here, that's why there's so many pins, is so that they can be kept separate. On the flip side of the coin, if you require them to be connected together, if you want all the grounds connected together, well, they're all broken out here on a header, and you can do whatever you like with them. And that's kind of the whole point. I've tried to add in as many different places as I can, places to break various signals out. There's the incoming and outgoing audio and a ground reference just here in a little 3-pin header. I've included some test points. I intend to write documentation in the future for testing this device and hacking it. All of these are in a 2.54mm pin pitch, or in old money 0.1 inch. And just because there's a gap here, we don't have any funny Arduino Uno stuff going on. If you set up a bit of variaboard that's 0.1 inch, it will marry up with these holes, and it will also marry up with these holes, and it will also marry up with all of the test points and all of the other headers. So they may look randomly spaced, but they are not. So if you want to set up some sort of a daughter board that sits over the top of this, you're not worrying about weird offsets and strange spacing issues. It's all 0.1 inch or 2.54mm. Okay, so I think the next part would be to show this actually running, because it's all very good and well getting a little red LED to light up, but might be helpful to see it run. Okay, so what I've got here is the interface is connected to one of my Supura mobile Tetra radios. That's off screen, and the radio that is going to talk to is the handset that you can see to the left of the screen, just sat on its side. So I've got the interface is connected also to my computer. It's running Zello, and I've got Zello here on a handset, one of these Chinese mobile phone jobbies. So I'm going to leave the room. I'll make a few calls just to show you this thing running. What you'll see is the red LED to show that the PTT has engaged. That will illuminate, and you'll see the radio light up and you'll hear the audio from that. Okay, this is a test. The test is all this is, and all I'm doing is testing.
The test is all this is. Test 1, 2, 3, this is a test.
Okay, so you can see that quite clearly works. I haven't spent a great deal of time tuning the audio in. I've just sort of thrown this test together to demonstrate that it physically works. Audio tuning is a separate matter entirely. What we'll do now is we'll make the reverse test. I'll put my Chinese handset on the desk, I'll take the Tetra handset away, and we should be able to do the exact same thing but in reverse. Okay, so this time around the audio is going the opposite direction, and so this time you'll see the green LED illuminate to show that the audio is going in the opposite direction. I'll leave the room now and I'll call up on the Tetra handset. One, two, three. This is a test. A test is all this is.
A test is all this is.
All I'm doing is testing.
All I'm doing is testing.
And a test is all this is.
And a test is all this is.
Okay, so the Vox in that direction is actually being handled within Zello. It's not on COM port keying. But you can see the behaviour that COM port keying would have through the green LED. That my Tetra radio does not have COM port keying. It doesn't have a port on there that is connected that could be used. It does have a port that could be used, but it isn't connected. So the way that is happening is the VOXLINK interface is detecting audio through the Vox circuit, and as a result is changing the state of the serial port, and it's illuminating the green LED to show that is happening. Okay, so the next thing I'll do is I'll show you the terminal window for debug information, just as an example. Okay, you'll have to forgive me for going handheld here, but there isn't an easy way of showing this. So I've got the Tetra handset in my hand. I've got the Chinese mobile phone device off to our left hand side. And what we're looking at here is my computer screen, and I've got a terminal window open just there at the bottom, and I've pointed that towards the serial port that is on the VOXLINK interface, and it's being fed sort of debug information from the microcontroller, and I'm having the microcontroller announce what the states of various different things is. So the column on the left hand side is the delay dial in milliseconds. So I'm just going to reach over here now and adjust the dial. I'm going to turn it all the way down to the bottom, and it's down to 200 milliseconds. If I turn it all the way up, just twisting it up, and that's the top there. So 5,315 milliseconds or thereabouts. Again, you can change the maths in the programming to adjust what the range of that would be, but nevertheless, turn it down to something a bit more sensible. Yep, that'll do me. Okay, so the next column, the second column, is the TX trigger state, and that is related to the third column, which is PTT state. TX trigger is the microcontroller seeing pulses from the VOX circuit, and when it sees those pulses it reacts to them on the basis of the delay dial. It will then set the PTT state accordingly. The fourth column is the RX trigger, which is audio going in the opposite direction. There's no sort of dial to adjust that, that's just in code. Again, that can be changed. I think that's set to 1000 milliseconds, so 1 second at the moment. And then to the right of it, RX state, which is rather than triggering the press to talk, it's going to trigger the serial ports and the green LED on the front of the interface. So if I key up with my radio now, 1, 2, 3, 4, 5, this is a test. A test is all this is. This is just a test, and a test is all this is. This is just a test, and you can see that RX state on the right hand side has gone high, and it doesn't catch all of the I think we're out in time a little bit. Okay, bear with us, I'll just dekey and let it relax. Okay, so I need to have a play with the timing here because it's not catching it exactly. So I'll go in the opposite direction and we'll watch what happens with the TX trigger. One, two, three. This is a test, and a test is all this is. Okay, so you can see it picking up pulses on the TX trigger side. I'll just turn this down. So when I start talking, the second column you can see it seeing pulses, and that's where it's showing TX trigger state high. The third column you can see PTT state has been set to high as a result of that, and it's staying high because it's looking at the delay dial. Okay, so that's an example of, you know, the kinds of things that you could do with the interface. You could do a whole lot more. I'm going to code updates in the future and make them available, but I'm sure I make no bones about it, I am not a programmer. I'm more of a hardware guy, and I'm sure you guys could do far better than I can. Okay, I think that's about it for now. Thanks for watching, and I'll post up something a little bit more polished in the future, and yeah, I will keep you updated as to just what's going on. Thanks for watching.